Black holes are the universe's most fearsome reputation, but not for the reason you might think. In fact, if our sun were to suddenly collapse into a black hole, the Earth wouldn't get pulled in. It would simply continue orbiting the tiny, incredibly dense object just as it orbits the sun now, feeling the same gravitational pull. The only difference? We'd be plunged into eternal darkness. This often misunderstood fact immediately sets the stage for a universe far more complex and terrifyingly fascinating than most people imagine. Today, we're diving deep into the ultimate cosmic enigma: black holes. Are they a hidden threat? What exactly are they? How do they work? And what about the closest one? Is it something we should actually be worried about? Prepare to have your mind stretched, because the truth about these cosmic monsters is far more profound than you might think. At their core, black holes are regions of spacetime where gravity is so incredibly strong that nothing, not even light, can escape once it crosses a certain boundary called the event horizon. They aren't holes in the conventional sense, but rather an immense concentration of mass packed into an incredibly small volume. Think of a massive star, many times larger than our sun, that has exhausted its nuclear fuel. Without the outward pressure from fusion reactions to counteract the inward pull of its own gravity, the star collapses in on itself. If its core is massive enough, roughly 3 times the mass of our sun or more, it will collapse indefinitely, squeezing all its matter into an infinitesimally small point called a singularity. This singularity is the heart of the black hole, where our current understanding of physics breaks down. The event horizon is merely the point of no return. Once you cross it, you're on a one-way trip, accelerating towards the singularity, and anything you send back, even light, can't make it out. The very fabric of spacetime itself is warped and twisted around this immense gravity well. It's not about suction, it's about spacetime curving so steeply that all paths, including those of light, lead inward. The density is so extreme that a mass equivalent to our entire sun could be compressed into a sphere no larger than a city like New York. This extreme density and the resulting gravitational pull are what make black holes so utterly captivating and terrifying. They are not empty voids, but rather regions where matter has been compressed to an unimaginable degree, creating the most extreme environments in the universe. Scientists primarily categorize black holes into 2 main types: stellar mass black holes and supermassive black holes. Stellar mass black holes are the remnants of massive stars that have died in spectacular supernova explosions. They typically range from about 3 to several tens of solar masses, meaning 3 to perhaps 30 times the mass of our sun. These are relatively common throughout galaxies, often formed from the demise of truly enormous stars. For example, Cygnus X1, one of the earliest and most studied black hole candidates, is a stellar mass black hole roughly 21 times the mass of our sun, locked in a binary system with a blue supergiant star. The gravity of the black hole pulls matter from its companion star into a superheated accretion disk, which emits powerful X-rays, allowing us to detect its presence indirectly. On the other end of the spectrum are supermassive black holes, which are truly gargantuan. These monsters can range from hundreds of thousands to billions of times the mass of our sun. Almost every large galaxy, including our own Milky Way, is believed to harbor a supermassive black hole at its center. Our galaxy's central supermassive black hole is called Sagittarius A star, or Skiar A star, weighing in at about 4 million solar masses. We know it's there because we can observe stars orbiting it at incredible speeds, their movements betraying the presence of an unseen, immensely powerful gravitational force. The existence of these galactic behemoths poses a fascinating question. How did they get so big? Current theories suggest they might have grown by accreting vast amounts of gas and dust from their surroundings, merging with other black holes or perhaps even forming from the direct collapse of colossal gas clouds in the early universe. The dynamics around these supermassive black holes are extreme. Immense jets of matter can shoot out from their poles, traveling at relativistic speeds, influencing the formation and evolution of entire galaxies. They are not merely passive objects but active participants in the cosmic ballet. Black holes don't just sit there passively. They are incredibly dynamic and play crucial roles in the universe, often acting as cosmic engines or regulators. When matter falls towards a black hole, it doesn't just disappear. Instead, it forms a superheated, rapidly spinning accretion disk around the event horizon. The intense friction within this disk heats the gas to millions of degrees, causing it to emit powerful X-rays and gamma rays, making these regions some of the brightest objects in the universe, even though the black hole itself is invisible. This process is how we detect many black holes indirectly. For active galactic nuclei, which are galaxies with incredibly bright centers, the light we see is primarily from the matter being consumed by their central supermassive black holes. These are the cosmic devourers in action, constantly feeding on their surroundings. Beyond merely consuming matter, black holes also have a profound influence on their galactic environments. Supermassive black holes can launch powerful relativistic jets of plasma, extending thousands or even millions of light-years into space. These jets, often observed at radio wavelengths, are thought to be powered by the spinning black hole and the magnetic fields within the accretion disk. These jets can heat vast regions of interstellar gas, influencing how new stars form. In some cases, they can even prevent star formation, effectively regulating the growth of their host galaxies. So paradoxically, these cosmic devourers are not just destroyers, they are also crucial architects, helping to shape the very structure and evolution of the galaxies we see around us. They are integral to the cosmic web, influencing galactic clusters and the distribution of matter on the largest scales. They aren't just isolated phenomena. They're deeply interconnected with the universe's grand design. Given their immense power, it's natural to wonder about the consequences of black holes for Earth. The short answer is, for now, no, not really. The biggest threat to our planet from a black hole would be a direct collision or coming too close to one. However, space is incredibly vast, and the distances between celestial objects are enormous. The closest known stellar mass black hole to Earth, named Gaia BH1, is located about 1,560 light-years away in the constellation Ophiuchus. While this sounds close in cosmic terms, it's an unimaginable distance in human terms. A light-year is about 9,500,000,000,000 kilometers. So 1,560 light-years is an immense cosmic buffer. At that distance, its gravitational pull is utterly negligible to our solar system. There's simply no chance of it sucking us in. What about Sagittarius A star, our own galaxy's supermassive black hole? It's located about 27,000 light-years away at the center of the Milky Way. Our solar system is in one of the galaxy's spiral arms, orbiting Sagittarius A star safely from a huge distance. While it's powerful, its influence diminishes rapidly with distance. Our orbit around the galactic center is stable, and there's no indication that Sesgar A** poses any direct threat to our solar system. The risk of Earth falling into Sesgar A* is practically zero. However, the consequences of hypothetical scenarios are fascinating to ponder. If a rogue stellar mass black hole were to somehow enter our solar system, the gravitational disturbances would be catastrophic. It wouldn't necessarily suck Earth in directly, but its immense gravity would perturb the orbits of planets, potentially flinging them out of the solar system, crashing them into each other, or sending them spiraling into the sun. Life as we know it would cease long before a direct swallowing. Another more theoretical concern is the potential for micro-black holes to be created in high-energy particle accelerators like the Large Hadron Collider. However, physicists overwhelmingly agree that if such micro-black holes were created, they would be incredibly tiny and unstable, evaporating almost immediately through a process called Hawking radiation, posing no threat to Earth. So, while the thought of a black hole is terrifying, in reality, our solar system is in a very safe neighborhood. Here's where things get truly wild and venture into the realm of controversial theories that challenge conventional understanding. Are black holes merely cosmic vacuum cleaners? Or could they be something far more profound, perhaps even portals to other universes or dimensions? The standard model of black holes, based on Einstein's general relativity, describes them as regions of spacetime leading to a singularity where information is seemingly destroyed. However, this idea of information loss troubles many physicists, leading to concepts like the holographic principle and the information paradox. A particularly provocative idea explored by some theoretical physicists is that black holes might be connected to white holes. A white hole is a theoretical region of spacetime that acts as the opposite of a black hole. Instead of sucking matter in, it violently expels it. While no white holes have ever been observed, some theories suggest that a black hole could lead to a white hole in another part of the universe, or even in another universe entirely, forming a sort of wormhole or cosmic bridge. This concept of eternal black holes, derived from certain mathematical solutions to Einstein's equations, suggests that an observer falling into a black hole might not hit a singularity, but could potentially pass through to another region of spacetime. This would be a form of cosmic tunnel. Now, to be clear, this is highly speculative and far from mainstream science. Most physicists believe that any such wormhole would be unstable, collapsing before anything could pass through, or that the intense tidal forces near the singularity would spaghettify anything attempting the journey. Furthermore, the information paradox suggests that information about what falls into a black hole isn't truly destroyed, but is encoded on the event horizon, implying no escape to another universe. However, the sheer mathematical possibility, even if theoretical, fuels fascinating debates. It challenges our perception of reality and opens up a dizzying array of questions. If a black hole is a portal, what lies on the other side? Could it be a gateway to the past, the future, or entirely different laws of physics? While there's no evidence to support it, the very idea of black holes as more than just gravitational traps, as potential cosmic transit systems, is one of the most mind-bending and deeply debated concepts in modern astrophysics. Pushing the boundaries of human imagination and our understanding of the universe's ultimate structure, it pushes us to question whether our current understanding of space-time is truly complete. As we journey through the cosmos, black holes remain among the most mysterious and extreme objects known to science. From the stellar remnants of exploded stars to the supermassive giants anchoring galaxies, they are not just cosmic oddities, but fundamental components of the universe's structure and evolution. While the idea of a hidden threat from a black hole is largely confined to science fiction for us here on Earth, their immense power and the bizarre physics governing them continue to challenge our understanding of space, time, and gravity itself. The closest cosmic devourer, Gaia BH1, poses no direct danger, merely existing as a distant testament to the violent end of a star. The ongoing research into black holes, from direct imaging projects like the Event Horizon Telescope capturing the shadow of Sagittarius A star, to theoretical explorations of quantum gravity and the information paradox, continues to unveil new layers of complexity. They are not just destinations for matter, they are laboratories of extreme physics, pushing the very limits of Einstein's theories and perhaps hinting at new, as yet undiscovered laws of the universe. What do you think about these cosmic giants? Does the thought of them fill you with dread or a sense of awe? Do you believe they hold secrets to other dimensions, or are they simply the natural end product of massive stars? The debate surrounding their ultimate nature and their role in the cosmos is far from over, and every new discovery brings us closer to understanding these profound enigmas. The universe, it seems, always has more surprises in